Hello and welcome to week 8 of Algebra. We're going to jump right in today and start with a warm-up that I do want you to complete in your math notebook. When I grade your notes this week, your weekly notes that you're submitting, I should see notes for this recording. And in those notes, I should also see the worked out warm-up problems in your math notebook. So make sure you've got your math notebook and you're ready to take good notes. So we are going to start with warming up with some linear equations. So remember, linear equations, usually in the slope-intercept form, it's y equals mx plus b. And when we graph a linear equation, guess what type of graph we get? We get a line. So in the warm-up questions below, you are simply going to solve for y in the equations below. You can kind of think of this as solving for some literal equations, but in fact these are linear equations. But you go about it the same way that you solve for literal equations, which we did earlier in the school year. So you are solving for y in the equations below. And remember, to solve for a variable, you're always going to do the opposite, or you're going to do the inverse operations to work on getting y all alone on the left side of these equations. You're solving for y. So go ahead and click pause and try these on your own. And then when you're ready to check your work with mine, go ahead and click play. All right, so we are solving for y in each of these equations. And again, these are linear equations. So to solve for y in the first one, we just need to move this term, this 3x. Move it over to the right side. And to move it over to the right side, we can just simply subtract it from both sides. So we'll subtract 3x from both sides. And we are left with y on the left side. This is good, that's what we're trying to do. And then 6 minus 3x, because these are not like terms. 6 is a constant, it's a whole number. And then we've got a variable term here with this negative 3x, or the 3x that we're subtracting. So we will stop there. We can't combine those any further. So that is our final answer. Y equals 6 minus 3x. Looking at the second equation where we are solving for y, we want to get y all alone, and y, we are subtracting 6 from y. So to get y all alone, we're going to do the opposite. We're going to add 6 to both sides. We're going to add 6 to both sides. That leaves us with y on the left side of our equation equals, we've got this negative 4x and we're adding 6 to it. Again, these are unlike terms. We can't combine them, so we're done. There's our answer. Y equals negative 4x plus 6. You could have written it as y equals 6 minus 4x. Same with up here. You could have written this as y equals negative 3 plus 6. It doesn't matter the order. The important part is, do you have all the correct terms in there and the correct signs in front of them? And that's it for our warm-up questions. Just getting in the habit of solving for y in some linear equations. And the reason we did that is we're going to look at graphing linear equations this week. And it's always helpful to have y equals format of our linear equations so that we can graph them. We always want to get it into y equals y or mx plus b form, and that's why we practiced solving for y in equations for our warm-up today. All right, so this week, as I mentioned, we're going to focus on graphing functions. We're going to look at graphing functions when we're given a limited domain. Remember, domain is all of our possible x values, our inputs. And we're going to look at graphing functions given a domain of all real numbers. So if we're going to do it two different ways where we have a limited domain, and then we're looking for how we can graph functions when we can have any domain, all real numbers. And then we're also going to look at arithmetic sequences, and I think we're also looking at independent and dependent variables, which is not on that list. So we're completing, I believe, 3 sessions this week. Yep. All right. Moving on. Okay, so I just mentioned that one of the things we're going to be doing is graphing solutions when we're given a specific domain. And remember, domain is our possible x values, or you can think of it as the input to our function. And we need to find the corresponding y values, or the outputs of that function. So here's an example of where we can graph solutions given a specific domain. So the question below, an example, says graph the function. This should just say graph, there's only one below. Graph the function from the given domain. So here's our function, 2x plus y equals 2. This is our function. And then here's our domain, and it's written as D, capital D. And then these are all of our possible x values that we're going to plug in to this function and get our corresponding outputs. So remember, domain is your x values or your input, where the range is going to be your y values or your outputs. So all we're going to do this is we're going to take each of our domains and plug it into this function to get our output. So right now it's kind of hard to see what the output would be because of the way the function is written. It's written as 2x plus y equals 2. Well, the domain is going to go into the x value. We're going to plug in our given domain values one at a time, and we want to find out what our y value is. But like I said, with it written like this, it's kind of hard to see what our y value would be. So what do you think we could do to this equation? Do you think we can rearrange it so that it's easier for us to see what our output value is? Yeah, let's solve for y. Let's just rearrange this function. We're not changing the function. We're just going to rearrange it and solve for y so that we can plug our domain in and then easily see what the output is. So this is just like we did in the warm-up, where we're going to solve for y. So I'm going to erase that stuff so that we can solve for y. We want to get y all alone. There's our y. So we're going to subtract 2x from both sides to solve for y. So we'll subtract 2x from both sides, and I get y equals 2 minus 2x. Or you could have negative 2x plus 2. It doesn't matter. So now it's written easily, so when we plug in each of our inputs in for x, we can easily see what our output value is going to be. So let's start. Our first value in the domain is negative 2. So let's plug in negative 2. Whenever we see an x, let's plug in negative 2. So y equals, maybe let's do this up here so I can have some more space. Y equals, actually maybe in here. Y equals 2 minus 2 times negative 2. And what does that give us? Let's do that work up here. And what do we get? Let's do some evaluations here. So negative 2 times negative 2 becomes a positive 4. So 2 plus 4 is 6. So we get 6. When the input is negative 2, we get an output of 6. And we can write this as an ordered pair so that we can plot that point. So we can graph it. So our x value is negative 2, and then the corresponding y value will be 6. So let's keep going here. I'm going to change color maybe just to help out. Now let's do when x equals 0, when x equals 0. So let's see if I can do it down here. 2 minus 2 times x, we substitute in 0. I know negative 2 times 0 is 0. Do the work up here. There's not a whole lot of room. So really we're taking 2 minus 0 equals 2. So that would give us the value of 2. So as an ordered pair, when we plug in 0, we're going to get 0, -2. When we plug in 0 for x, we get our y value will be +2, not -2, sorry. So again, that was +2. So we're going to keep going. So when we plug in, let's change colors here just to kind of, when we have a x value of 2, so y equals 2 minus, plugging in for x, we're going to plug in 2. Do the math. 2 times 2 is 4, so we're really taking 2 minus 4 equals -2. So when our x value is 2, our corresponding y value will be -2, which means our ordered pair will be 2, -2. One more to go. The last domain value is 4. Let's change the font color again. We haven't used a pink color. So when we have 4 for x, down here, so y equals, the function is 2 minus 2 times x, and now we're plugging in the 4 there. So we've really got 2 minus 8. 2 minus 8 is -6. So when the x value is 4, then our y value will be -6. So again, we're going to stop here now because we only were given 4 different domain values. So we're going to have 4 corresponding y values. And now we can plot our ordered pairs. So let's go ahead and plot our points. So the first one is at -2, 6. So we can go ahead and plot -2, 6. I'm just going to do this all in black here. Well, let's do it in blue so it shows up on the graph. I'm going to do all the colors or points in the same color. So -2, we start at our origin, we go to the left -2, and then we go up because it's a +6, and here's our point. I can label that. Our next point is 0, and then up 2. So here's our next coordinate at 0, 2. Our next coordinate is at 2, -2, +2, -2, so to the right 2, and then down 2, and then the last point is at 4, -6, so right here. So we are not going to connect the points because we are only given these certain numbers to plug into our function. So we are not going to connect the points here only because we're given some specific domains. We're only given 4 inputs, and then we should have 4 outputs. So we're only going to have 4 points. Now, I'm going to go on to the next slide. So if you need more time, go ahead and click pause. If we are graphing a function for all real numbers, this is when we're going to get a line when we graph. Because we're not given just a set of a couple specific domain values. It's telling us graph the function for all real numbers. So it's going to include every single possible value that we could plug into this function. So when we graph it, we're going to get a line. So whenever you are graphing a function for all real numbers, you're going to get a line when you graph it. But in order to graph our line, we need to plot a couple points that will allow us to then know the direction of the line and draw on our line. So we're still going to go about this very similarly as to what we did on the previous slide, is that we're going to pick some points and pick some endpoints and find our outputs, which will create an ordered pair. And then we can plot those points and draw in a line. All right, so let's do that. We're going to graph the equation y equals 2x minus 4. So this is nice because it's already written where we've got y all alone, so that it's really easy when we plug in a value for x, when we plug in an input value, it's really easy then to see what our output value would be. So we already have this equation. We don't need to rearrange on anything. It's ready to go. So we're going to use a table that helps us graph this equation. So I'm going to choose a couple input values. It's always easy for me to choose 0. I'll choose some in the positive direction. How about 2 and 1 in the negative direction? And we always want to have at least 3 points. 2 is not enough. 2, the line it's hard to draw in, but when you have 3 or more points, that's going to give you an adequate number of points to draw on a nice line. So I'm going to choose 0 and 1 in the negative direction and 1 in the positive direction. So if my input value for x is 0, I'm going to plug 0 in whenever I see an x, and then I'm going to evaluate. So 2 times 0 is 0, minus 4 is minus 4. So the output value would be -4 here. And as I can write that as a ordered pair as 0, -4. There's our input, and there's our corresponding output. What about when we plug in 2 into this equation? So y equals 2 times x. I'm going to plug in 2 for my x, minus 4. So 2 times 2 I know is 4. 4 minus 4 is 0. So the output would be 0. So when I plug in a 2, I get 0. Keep going. Y equals, now I'm going to plug in a -2, minus 4. -2 times 2 is -4. -4 minus 4 is -8. So my output value is -8. So when I plug in -2, I get -8. Now let's plot these points. So 0, -4. There we go. And then we've got 2, 0. So move to the right 2, and we're not going up or down. We stop right there. And then -2, -8, which falls right down here into that words. So now you can see all the points line up. So I know I did the math right. If you ever have a point that's kind of out here, you know you might have done something wrong and you want to check. So now let's connect our points and draw in our line. And again, we're drawing a line to show every point. Whoops, I kind of missed that. It's hard for me to draw a line in here. And then put an arrow to show that our line can keep going on each end forever, and that literally every single point that lies on this line could be work for this function. You'd have your input and your corresponding output. Remember, points are always written as x, y, so any point on this graph means that the x value would be your input and your y value would be your output of this function. And any point on this entire line would work for this function. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. Arithmetic sequences. So I'm quickly going to introduce this idea. I don't want to make this recording too long. So an arithmetic sequence is a type of pattern. It's a pattern. So here's some examples of patterns we can have with numbers. It's just a list of numbers. So a specific type of pattern of numbers is an arithmetic sequence. And in order to be an arithmetic sequence, the difference between each number has to be the same. So when I say the difference, look at this example here. So this is an example of an arithmetic sequence. So it says 1, 3, 5, 7, 9, and then it can keep going. The dots mean the pattern can keep going on and on and on. So how do we go from 1 to 3? We're adding 2. How do we go from 3 to 5? We're increasing by 2. How do 5 to 7? We're increasing by 2. 7 to 9. Guess what? We're increasing by 2. So because the difference between each of our terms, and that's what we call the numbers in our arithmetic sequence, we call each number a term. So the difference between each term is increasing by 2. So since it's increasing by the same amount each time, that means it's an arithmetic sequence. Let's look at this next arithmetic sequence, this pattern of numbers. So how do we go from 10 to 7? Well, we're decreasing, right? We're decreasing by 3. How about from 7 to 4? Decreasing by 3. 4 to 1, we're decreasing by 3. So again, we're decreasing the same amount. So that increase or decrease between each term is called the difference. We call that the difference when we're dealing with arithmetic sequences. So we call this the difference. And I'm going to go to the next slide now. So if you need more time, go ahead and click pause. So let's now look at some patterns and determine if the patterns are in fact arithmetic or not. And if it is an arithmetic sequence, we're going to determine the difference. So let's look at the, oh, actually go ahead and click pause and try this on your own first. Go ahead and click pause and try this on your own. All right, so from 0 to 3, how much are we increasing by? 3. So let's see if this is the same amount each time. And it looks like it is. So that means if each of these are increasing by 3, which is the same amount each time, this is, yes, an arithmetic sequence. And because it's an arithmetic sequence, it does have a difference that is equal to 3, positive 3. What about the second pattern of numbers? So here I see I'm going up by 4, increasing by 4. 6 to 8, though, I'm increasing by 2. 8 to 9, I'm increasing by 1. So already I'm seeing that there's not the same difference. So this is not an arithmetic sequence. I'm going to go on to the next slide, so if you need more. Oh, and by the way, guys, in order to be an arithmetic sequence, it has to increase and decrease by the same amount, and that's going to be either by adding or subtracting the same number. Arithmetic sequences will not be multiplied or divided by the same number, so we're only dealing with adding and subtracting to find the same difference, okay? When we use multiplication and division, that's a different type of sequence. So when we're dealing with arithmetic, it's only finding a difference that's either added or subtracted the same amount. So I'm going to go on the next slide. And I'm not going to go over this. I'm going to save this for you guys to learn in your Schoology lessons this week, but I wanted to make sure we understood what the difference is because you're going to be using a formula with the letter D in it, which stands for difference, the common difference, which is, again, with the same value that you would add or subtract from each term in the pattern. And you're going to learn a cool formula that when you're given the first few terms of a sequence and then you're asked to, let's say, like find the 20th term of the sequence or the 40th term, you can use this formula that you're going to learn about to find it instead of going through and adding the difference 20 times to find the difference. You can just plug it into a formula and really quick find the 20th term or the 30th term or the 40th term. So you'll learn that in Schoology this week. So we're going to go on now and complete the key phrase assignment. So you got 2 questions asked this week. The first one is there something important on Wednesday that you need to do this week? So what is that? What do you need to do on Wednesday, October 3rd of this week? And then the second is I have a pattern below, and is this pattern an arithmetic sequence? Why or why not? Make sure you're answering why or why not to get full credit for that. And that's it. So have a fantastic rest of your week, and if you need any help with anything, let me know. I'm here to help.